Hi, my name is Karina Patel, and this is Lab 2 for Physics 1 Projectile Motion. The purpose of this lab is to compare the projectile motion of an object to a computational model based on gravity, and then again based on drag and gravity. And the computational model we used is GlowScript. The experimental model used was Tracker, and then the physics principle used is Newton's second law, drag force, and gravity. So these are the preview of the results. This graph is from the results from the Tracker model with x and y on the x-axis and then time on the y-axis. And the assumptions we use is that there's only gravity and drag force, no others. And we use these assumptions to create the vector force FNet in GlowScript. So the main physics ideas is average velocity, which is then used to calculate the average velocity for the position update formula. And then the velocity update formula, we use the FNet from the drag force and the gravitational force to calculate acceleration. And then the drag force is on the bottom right, and that is used in the FNet calculations. And then for gravitational force, we just use the 0 negative ball's mass times gravity constant. So the setup is our system is a paper ball, the surroundings are the drag force and the gravity, and then the initial time is 0.7 seconds, the delta t is 0.03 seconds, initial position is listed here, and then initial velocity is also listed. And to find the initial velocity, we use v average, and then we use the formula from the previous slide. And on the right is a screenshot from our video where we threw the paper ball in class. So this is my code. This version has drag included. As you can see, b equals 0.0028. And then in the version with just gravity and no drag, b would equal just 0. And then on the right, you can see FG is listed, FD is calculated, and then under that, FNet is the addition between FD and FG. This is a computational model on the left and the experimental model on the right, and these are our results. So the top graph in the computational model is just the gravity included, and the bottom one is the gravity and the drag included. And then you can see that the model with just gravity is very similar to the experimental model, while the drag and gravity model looks a little different. So possible error that caused the drag model to look a little different is that the measurements could be inaccurate on Tracker. Our calibration steps could have been inaccurate. Tracker is very old and could have had its own technical errors. And then lastly, there could have been some calculation errors on mine and my group's part. So for the what does it mean question, we can see that the velocity versus time graph on the top is just from the gravitational model, and the velocity is a straight line, and when velocity is constant, that means that FNet equals 0. So the gravitational model predicts the terminal velocity because velocity is constant. And then on the graph on the bottom right, that is from the drag and gravitational model. And this does not predict the terminal velocity because velocity is changing. So if you want to find the terminal velocity of the experimental model, use the computational model with just gravity and not gravity and drag. So for the what if question, if the ball was thrown in a vertical up and down trajectory, the time taken for the ball to fall would be the same because drag does not consider the angle that the ball is thrown in its equation. So if it was thrown at any angle versus just in a straight 90-degree angle, that doesn't matter in the final equation for the forces, so the time would be the same because it would have the same calculations. Also, constant gravity is acting on the y components of the vectors in both situations, so overall the time taken would be the exact same in both situations. And you can see with the F drag equation on the bottom, the angle is not involved in this. So in the conclusion, this lab supports our knowledge of gravitational force, drag force, and Newton's second law. Thanks for watching.